So we got a couple of different methods for determining the equivalence point. So one is to use a pH meter to monitor the pH and then plot that titration curve. The center of that vertical region where it's rapidly changing is going to be the equivalence point. If we took a derivative, right, took the first derivative, we're going to end up with a peak there because that's where it's rapidly changing. Right? For those of you who are taking calculus, right, you'd be like, oh yeah, I remember what that stuff is. Or we could use an acid-base indicator, which marks the end point of a titration by changing color. So this is section 14.5, where we're going to look at these indicators. And that's how you're practically going to do a lot of these things, because adding an indicator is easy, it's quick, it's fairly reliable if you pick a good acid-base indicator for your reaction. And that endpoint and the equivalence point are going to be pretty close. The pH meter is way more definitive, but means you've got to do this lengthier titration where you're plotting out multiple points to give you a titration curve. Whereas here you're just titrating until it changes color. So this has an advantage of being fast, right? And your endpoint is about going to be equal to your equivalence point. Right? So oftentimes it's good enough. So here's an example of an indicator, phenolphthalein. Right, you will probably do a titration with phenolphthalein. Everybody loves the phenolphthalein. Cool thing about phenolphthalein is that it goes from clear to pink at about pH 7. So a lot of these things that have an acid or a base that neutralizes around pH 7, the phenolphthalein is going to be a good indicator for that. It's got two forms. One where it is protonated. Right, and so you got this little proton up here, and another one where it is deprotonated. And this actually is a weak acid, weak base conjugate pair. So that's one of the cautions about dealing with indicators is if you put in too much, you're going to change the pH of your solution because you're going to end up titrating indicator more than you're going to titrate the thing you're interested in. Right? The other cool thing about phenolphthalein is that it used to be an active component in X-Lax, which is a laxative. So this is a case where you do not want to lick the science. Let's look at another example. So bromothymol blue, which is an indicator with a Ka value of 1 times 10 to the minus 7, is yellow in its protonated form and blue in its base form. Suppose you want to put a few drops of this indicator into a strongly acidic solution. If the solution is then titrated with sodium hydroxide, at what pH will the indicator change first be visible? So when you first put it in there, right, you've got something that is in an acidic solution. And so it's going to be yellow. And then you're going to titrate until it turns where you've got equal amounts of acid and equal amounts of base. So if it's blue in its base form, so if I push the pH all the way down, all the way up to like 14 by adding in a bunch of sodium hydroxide, and then it would be blue. If I had it all the way down at like 2 with a strong acid, it would be yellow. So where I've got a neutral reaction, yellow and blue make green. Right? So we're going to titrate until it turns green. And the question is, at what pH is that going to first happen? And that's going to be related to what the Ka value is of that indicator. So we're going to assume that a noticeable color change is visible when our ratio is in a 1 to 10 configuration. Right? That's when we're going to first notice that color change. And that's because our eyes are actually going to work on a log scale. So the human eyeball is kind of a log-based, it's supposed to be an eyeball, give it some eyelashes there. It's a log-based sensor, right? So it's going to be log-based, which is why things are going to go in powers of 10. And when you look at magnitudes of stars, right, a magnitude 1 star is going to be 10 times brighter than a magnitude 2 star. We're going to assume that we can first see the hint of a greenish tint, yellow and a little bit of blue, when the solution is 1 part blue and 10 parts yellow. All right, so A is going to be our acid form. C is going to be our base form, and this is going to be our neutral form, right? And it's going to first start to be greenish when it's a 1 to 10 form. So we're going to replace this 1 to 10, right? This is going to be our, for your indicator, do an IN, so HA, you could use HA, or you could do IN. It's just the same thing. You're just calling it IN instead of A, right? And then this is going to be our IN minus form or A minus form. Conjugate acid, conjugate base. Our indicator is going to be a weak acid, weak base. So our H plus concentration is going to be 1 times 10 to the 6th, or at a pH of about 6. So our color change is first visible at a pH of 6. Methyl red indicator is yellow in basic solution and red in acidic solution. So you're looking for a color change to happen around when it turns orange, right? So, and that's going to happen when you're right around the pKa of that indicator. So you got to look at the table of where the pH indicator changes colors, and then you've got Ka values, you're going to match those up. In a strong acid, strong base titration, the indicator color changes are going to be sharp, right? Because you're going from something really low for a strong acid, it's going to shoot up, and then it's going to become something really strongly basic for right? And with a weak acid, weak base, might be a little bit trickier to see, right? So it's going to be less sharp. A single drop of titrant in a strong acid, strong base will be enough to flip that color. There's a wide choice of suitable indicators out there. The results are going to agree within 1 drop of titrant using indicators with endpoints as far apart as pH 5 and pH 9. In a weak acid, the weaker the acid being titrated, the smaller the vertical area around the equivalence point, littler hump in there, which gives you much less flexibility in choosing the indicator. So if you've got something like phenolphthalein, which is going to change around 7, that it's not going to work. So here's a nice little table of useful pH ranges for several common indicators. So if you've got something that changes around pH 7, right, you're going to match up the pKa of your weak acid to the pH, and you're going to look for something that's going to exhibit a color change around there. So bromethyl blue works well for something that would have a pKa of around 7, or 1 times 10 to the minus 7 as your Ka. You could probably get away with nitrophenol or phenol red. Good old phenolphthalein would work too, because you're going to be within plus or minus 1 pH unit. Right? So you want your indicator's pKa to match the pKa of the acid or base you're looking at to be within plus or minus 1 Ka unit.